So, actually both my tutors scolded me a lot yesterday for being so irritable, and they have threatened that if I get irritable again, they'll put that fan on. So today I'm going to smile. So anything you say or do, I will smile. So you better take advantage of it. Now, we were talking about fermions, and I just want to slightly modify one usage of a term. When we talk about gamma matrices, we say sometimes Weil representation and Majorana representation, and there was a third one which I gave in the beginning. Now, they are all equivalent, which means they are simply similarity transforms of each other. So it's better to call them basis rather than representation. Okay? Because a representation, there could be different representations of the Clifford algebra. For example, it has not only 4x4 representations, but also has 8x8 representations, which we haven't written down. So those would be different representations, while the same representation in different bases should be called just a change of basis. So Majorana basis, Weil basis, and so on. And I also need to say that this condition that gamma 0 is Hermitian and gamma I is anti-Hermitian, you can change that by change of basis if the change of basis is not unitary. If it's not unitary, then the new gammas will not be Hermitian or anti-Hermitian. This was brought to my attention by Nimani. But for this reason, it's not a good idea to make those change of basis. So when you consider basis of gamma matrices, you should simply consider one basis and all unitary transforms of that basis. Okay? And in that case, you are guaranteed that in all these family of bases, including the Weil and Majorana bases which I gave you, the gamma matrix gamma 0 is Hermitian and gamma I is anti-Hermitian. This property doesn't follow from the Clifford algebra. From Clifford algebra, we only know that gamma 0 squared is +1 and gamma I squared is -1. So if they have any definite hermiticity, then they must be Hermitian and anti-Hermitian. But in principle, any similarity transformation can be done. Okay. Now, one comment I wanted to make about the Majorana representation before I go on. It gives us, this is not commonly, this point of not representation basis. This point is not commonly made in books except books on supergravity of all things, books or articles. So, there's an amusing fact which occurs if you think of Majorana spinors. So first of all, remember Majorana basis is the basis where the gamma matrices are imaginary. Therefore, spinors can be real. That doesn't mean they are real. We are still free to choose complex solutions. If we choose them to be real, then they are called Majorana spinors. So Majorana spinors are those which are real in the Majorana basis. Now if you make a similarity transform, they'll have some property in every basis, which would be the analog of being real in Majorana basis. And they'll still be Majorana spinors. They can be Majorana spinors in any basis. Physically, what do they mean? Particle which is equal to its own antiparticle. Let me write these down. So the property is real. So Majorana spinors real in Majorana basis. So psi star is equal to psi. In any other basis, they have a property like psi star equals some matrix times psi. So that matrix happens to be 1 in this basis, and it will be something else in other basis. But it still says that psi star is related to psi, which means that psi and psi star are not independent fields. Okay? And we already know from our study of scalar fields what this means. It means physically that particle is equal to antiparticle. They are the same. Now an antiparticle has opposite electric charge from a particle. So this tells us that a Majorana particle has no charge. There is another way to see it. Charge is related to a symmetry under change of phase of psi, e to the I alpha times psi. Now you can clearly see that this relation will not be preserved by a phase, because e to the I alpha here, e to the minus I alpha here will not preserve the relation. So it means there cannot be a symmetry in such a theory under phase transformations, and so there cannot be a charge. So if at all there are any Majorana particles in nature, they can only be the neutral ones. So which fermions are neutral? Neutrinos only. So neutrinos have a possibility to be Majorana, and people are still debating that. It's still an open possibility. It's not settled. The whole issue of what neutrinos exactly look like is somewhat unclear. We know a lot of things about them, but in particular their masses, we have only learned something about them in the last decade or maybe even last 5 years, and it's still not settled. So there's a chance that this describes neutrinos. Okay, now let me come to this interesting property. Let's look at the mass term for a Majorana spinner. So what is the mass term? Of course, in general, the mass term in the Dirac-Lagrangian is m psi bar psi for any spinner. So it will also be so for a Majorana spinner. Okay? Now, in the Majorana basis, we can write this. So first of all, this is equal to m psi dagger gamma 0 psi. Okay. Now in the Majorana basis, psi dagger is the same as psi. So this is m psi a gamma 0 a b psi b. Now please look up in your notes to see whether gamma 0 is symmetric or antisymmetric in the Majorana basis. Hopefully it's antisymmetric. What was gamma 0 in the Majorana basis? So is it antisymmetric? Is it an antisymmetric matrix? Yes or no? I'm smiling. Huh? Yes? Everybody? Yes? Good. Okay. So gamma 0 is antisymmetric. So what does this tell us? That's very puzzling. It looks very puzzling, right? Since gamma 0 is antisymmetric, it seems to say that there is no mass term for a Majorana particle. But that's not a correct conclusion. That's why I put a question mark. Okay, you may say we can live without a mass term. Maybe there's some physics saying that there are no masses for such particles. Okay, now let's look at the kinetic term. Psi bar I gamma mu del mu psi. So this is I psi for a Majorana. Gamma 0 gamma mu del mu psi. Now again, if you do your exercise, you will find that gamma 0 gamma mu is actually symmetric in the Majorana basis. Okay, the first one is 1. Of course, if mu is 0, then this is 1. The other three are gamma 0, gamma I. You can easily calculate them, and you will find all are symmetric. In that case, so this is A, B, B. So this, in that case, is equal to I by 2 del mu of psi A, gamma 0, gamma mu, A, B, psi B. So we seem to find that for Majorana spinners, in the Majorana basis, the mass term is 0 and the kinetic term is a total derivative. So that's pretty much the end of it, right? No Lagrangian at all. So this is worrying. Okay, I find it very worrying. Now this will also be true for a Majorana spinner in any basis, because these things are basis independent. Okay, it will just be that in another basis, psi dagger cannot be replaced by psi, but if the Lagrangian is a total derivative in one basis, it will be a total derivative in all bases. Similarly, if the mass term vanishes in one basis, it will vanish in all bases. Now, there is really only one solution. Assume that the classical field psi of x satisfies this relation. That is not an ordinary field variable which has real or complex number values, but it has some strange kind of values which are anti-commuting between two different fields. We haven't done any quantization. This is all classical discussion. There are no commutators or anti-commutators here, but we should assume, in order to save ourselves from this problem, we should assume that psi A psi B is minus psi B psi A even at the level of classical fields. Okay? Now, there is a kind of number called the Grassmann number, and it means that fermion fields should be valued in the Grassmann numbers, classically. Okay? This fact is of great importance when you do the path integral approach to field theory, which I am not discussing in this course, but sooner or later you are bound to do it, because probably you know that in the path integral, what we do to get quantum mechanical answers is not to have operators and time ordering, but to integrate over classical configurations. All classical configurations, with the dominant one usually being the one closest to the solution of the equations. And then all the others contribute some quantum corrections. So, what are the classical configurations of fermions becomes very important in path integral language, and this teaches us that they must be classical objects which anti-commute. In fact, in path integral, there are no quantum objects as such. There are only classical fields, and then we do some integrals over them. Right? So, this becomes very important. And from the operator point of view, this says that when we quantize, we should use anti-commutators, because after all, the quantum bracket, whatever it is, should have a classical limit. I can always put h bar going effectively to 0. So for scalar fields, I had pi comma phi equals I h bar delta. If I put h bar equals 0, I just find that phi and pi commute, which is natural. Now here, because of the upper equation, when I put h bar equals 0, I should find that psi and psi anti-commute. Therefore, the quantum bracket should be an anti-commutator, which means I should quantize pi of this, comma, pi a at t and x, psi b at t and y, equals I. H bar is understood, though we don't normally put it, because we have set it to 1. And this curly bracket means that it is this times this plus this times this. Pi will in fact turn out to be psi. We have already seen that. Pi is the same as psi, or I psi. The canonical momentum to psi is psi, or psi dagger. So we'll find that psi dagger with psi, anti-commutator is this, and in the limit h bar goes to 0, then we'll find that psi dagger psi plus psi dagger is equal to 0, which is basically this relation for psi and psi dagger. Now there's only one little misleading thing potentially. This looks like it's a problem only for Majorana spinors, but actually this we must assume for all spinors, not only Majorana spinors. If you like, this is only a hint of the problem. Basically, if you try to do anything else other than anti-commutators, you'll end up in trouble sooner or later. But with Majorana spinors, you'll end up in trouble as soon as possible, namely the Lagrangian itself would vanish if you do the wrong thing. For this, we said let's take phi, and then let's try to find a fixed momentum mode of it which satisfies the Clangordin equation and then expand over that. So what's the fixed momentum mode? E to the minus I k dot x. It satisfies the Clangordin equation if k squared equals m squared. And then we put a summation here and put some oscillators. And then we had A as well as A dagger. Then we had maybe 1 over square root of 2 omega normalization, and then we integrated in k. The starting point, this was the free particle solution, as it might be called. That is, it was a solution, individual solution of the wave equation, Clangordin equation. So now for fermions, we need to find free particle solutions, and whatever we find, of course they are solutions of the Dirac equation, whatever we find, we'll put them in multiplied by oscillators, and then we'll quantize the oscillators, again by anti-commutators. Now the difference is that a fermion has an index, so the free particle solutions are not single functions like e to the minus I k dot x. This was okay for scalar fields because they were just single fields. So the free particle solutions were single functions. For fermions, we need to assume that we have some spinor function, which I'll call ua of k, and then e to the minus I k dot x. And I'll assume right from the beginning that k squared equals m squared for a reason which I think I showed you last time, which is that if the field satisfies the Dirac equation, then it also satisfies the Clangordin equation. This I showed last time. Each component does that. And that fact means if Clangordin operator acts on this, it says that k squared is m squared. Clangordin operator is not interested in this spinor coefficient. But Dirac operator will act on this because it has the gamma matrix structure in it. Okay? And today the resonance is here. Has anyone figured out the physics of this? Something to do with quantized fields, that I'm sure. But what, I don't know. Huh? Okay. Radiation field in a cavity. Okay. Anyway, so to find UK, so the point is that this is good because it already satisfies Clangordin equation, but some kind of structure of UK is needed in order to also solve the Dirac equation, which is a stronger equation. Okay. So it's very easy to find that because now Dirac equation, what will it do? It's I gamma mu del mu minus m is the operator acting on this. So this is going to give me the del mu is going to pull down minus ik combining with this I. So I'll get k mu gamma mu k mu minus m, which is a matrix AB on UB. So I shouldn't put this in here. Has to be 0. So this is the constraint on U. U has to have some dependence on k such that this operator kills it. Okay? Now this is easy to solve, most easy to solve by going to the rest frame where k mu is simply m 0 0. Okay? With fermions, nothing too special happens when m is 0 or non-zero, so we can as well take it generic and non-zero and do all this stuff. And later we'll get a Lorentz invariant expression, and then it can also be massless if we want. With gauge fields, vector fields, it's a problem because if m is not 0, then gauge invariance goes and the whole theory gets messed up. So doing this kind of analysis for vector fields is more difficult because we don't have a choice of rest frame. Of course, we have a choice of a good frame anyway, but here the rest frame is best. So what does that tell me? That mk0 minus m on u equals 0. Sorry, m gamma 0. That's what I meant to write. So gamma 0, k has only a k0 component, so this, which means 1 minus gamma 0 on u equals 0. So we see that these free particle solutions will depend on the frame, on the basis of gamma matrices, because now I have to put in gamma 0. So we'll work in the while basis, which is particularly transparent for physical quantities. And in the while basis, gamma 0 is 0, 1, 1, 0. Okay, so what is 1 minus gamma 0? It's the 4 by 4 matrix. 1, minus 1, minus 1, 1, which you can painfully write out like this. This condition says that u is a zero eigenvector of this matrix. Now by inspection you can see what are the zero eigenvectors of this matrix. Let's look at, there are precisely two of them. One is 1, 0, 1, 0. Because when you multiply here, you see this and this give a cancelling contribution. Same thing happens in this row, and this row and this row are unaffected because this has zeros there. So it's very easy to see that this is a zero eigenvector. And the other one is 0, 1, 0, 1. So both are zero eigenvectors. So these are the u's that we want to put in as free particle wave functions. But of course, only in the rest frame. Okay? So the most general u is a linear combination of those two zero eigenvectors. So it's A times 1, 0, 1, 0 plus B times 0, 1, 0, 1. So it is A, B, A, B. Now notice the repeating pattern A, B, A, B. This tells me that it's two component spinors. In this course I'll use chi to represent two component spinors. So any 4 component spinor obviously can be written as two different 2 component spinors, but for the free particle we see that you get same 2 component spinors. That's the property of those two zero eigenvectors. Good. Now we should normalize u of k. So we normalize. This is very convenient for future calculations. So u of k we normalize as root m or root 2m, root m chi, where chi itself is normalized to 1. You should be very clear where all the indices are. So this has indices which go over 1 and 2. This has also independent indices going over 1 and 2. So chi dagger chi is a dot product of a 2 component complex vector with its own complex conjugate. So this is a normalization. Okay. Now once we've done this, then it's very easy to go back to a general Lorentz frame. So for that, you need to pick k mu equals E0, 0, k3 with E squared minus k3 squared equals m squared. A general Lorentz frame can still be such that the momentum is taken along the z-axis, that just by rotation. So this. In this case, I'll leave as an exercise, you can try it in the tutorials. You will find that U of K is actually the following matrix, root of sigma mu k mu on chi. This is a 2 by 2 matrix, and root of sigma bar mu k mu on chi. And you can see that, okay, what are sigma and sigma bar? I was supposed to define them last time, but I forgot. But they are the convenient basis in terms of which the Dirac equation gets expressed in the Y basis. There is just 1 and 3 Pauli matrices, and sigma bar is 1 and minus the 3 Pauli matrices. Do these satisfy a Clifford algebra, sigma mu? I promise I'm smiling, but this you're giving the wrong answer. Please think. What is the Clifford algebra? In a Clifford algebra, every matrix anti-commutes with every other matrix. Does one anti-commute with any matrix? Does not, cannot. It's one. These do not satisfy a Clifford algebra. Instead, what happens is this with this satisfies a nice algebra, which implies that the 4 by 4 gamma matrices satisfy the Clifford algebra. If these had satisfied the Clifford algebra, we'd have found it long ago, right? Why would we have ever written 4 by 4 gamma matrices? We would have settled for 2 by 2 gamma matrices, but there isn't any such thing. Okay. Good. Now, what are these funny square roots? Well, it's easy to, so square root of a matrix, of course there's a sign ambiguity, but that we can fix somehow. It's something such that if I square it, then I should get that matrix. And it's easy to see because of the structure of Pauli matrices that you get root of E plus K3 1 minus sigma 3 by 2 plus root of E minus K3 1 plus sigma 3 by 2. This is root of, these are all left as exercises, and so here we have some minus signs, so it's plus with plus and minus with minus. So it's a very easy exercise. If you square the right hand side, you will get sigma mu k mu, where k mu is this 4 vector, the specific 4 vector. Good. Okay, now going back to this basis 1 0 1 0 and 0 1 0 1, we therefore have found that in a generic situation there are two independent U's, which are U, I'll label it U upper 1 of K. This is obtained by taking this stuff when chi is 1 0. So this is 1 0 1 0. Then I multiply out those explicit matrices with 1 0 and 1 0, and whatever I get, that's one of the possible two U's. So this is root E minus K3. Is really boring exercise and very, very simple. I wonder if it's even worth doing in tutorials, because anyone can do it for themselves. The other one, anyone can do it for themselves, but they may make sign mistakes, which I also might make. 0. Okay? So this is the solution for free particle wave functions u1 of k and u2 of k. And now what we are saying is that when we make a mode expansion of psi to quantize it, we should multiply u1 of k with its e to the minus I k dot x, of course, and an oscillator A dagger 1, and U2 with another oscillator A dagger 2. Okay, and what do these two different oscillators A dagger 1 and 2 do? They create spin up and spin down states of the same particle. Okay, so you should think of U of this index 1 and 2 as a spin index. And in a moment we will write the mode expansion. So U S K equals free particle solution for momentum K and spin S. Spin S really means spin S by 2, I suppose. S is just a label of the spin. It's S equals 1 and S equals 2 is spin up and spin down. So it's plus half and minus half. Because it will turn out that this field has spin half. Do you remember that when we studied scalar fields, we noticed that there is no spin degeneracy in the mode expansion? And that's why we said, well, they must be scalar fields. So here is a spin degeneracy, and that's why we can be sure that these are not just scalar particles. Not only that, you can see that, okay, I think that's enough that I want to say about that. Now you can also calculate from, if you are given 4 component spinners U, then you can also calculate U bar. So just once let me do it. U bar is obtained by doing what? In principle it's the dagger and then gamma 0, but dagger is just the transpose, and then you just have to multiply on the right by gamma 0, and you get some row vectors which are not very exciting, but they are like this. Again, simple exercise. The point is these are very important for actually doing calculations. That's about what you can say. And it's all in the notes which are already up on the website. So you can look for it there. Now a nice exercise, and this is again a result that's often used in calculations. U bar 1, U1 is just 2m independent of k. If I just take this and contract it with this, then I get e squared minus k squared square root, which is m. And then the other term gives me another m. When I add the m's, I get 2m. But in fact, the more general relation is that if this is a spin value r and this is a spin value s, then it's delta rs. So u bar 1 and u2, those give you 0. That also you can explicitly check from what's on the board. So when evaluating Feynman diagrams, you will often encounter, you will have the need to know these things, and although these depend on k, this particular inner product doesn't depend on k. Okay. Now, let me stress that U is the free particle solution also in the literal sense that it applies to the particle rather than the antiparticle. Okay. Roughly speaking, you can think of psi, that is the Dirac equation, as giving the particle, and the complex conjugate equation as giving the antiparticle. What's the complex conjugate equation? For that we should solve I gamma mu k mu plus m instead of minus m. At some point somebody had asked whether m is positive, whether the sign of m is important. And you see here that it's not important because one sign of m appears in the Dirac equation and other sign appears in the complex conjugated equation. Now the solutions of this will be slightly different, so they have the name V of k, and V of k are the free antiparticle solutions. And I hardly need to go through all this calculation, you can just repeat it. There are only a few extra minus signs, so you can find V R of K. No I. Thank you. No I. Good. V R of K as well as V bar R of K. And the new result, analogous to this one, is that V bar R, V bar S is minus 2m delta R S. No matter what any book might say, this does not mean that antiparticles have a negative mass. Everybody has a positive mass in this theory. Sorry, that's a mistake. Okay. There are also some completeness relations which may be useful, so let me write one of them. If I take U A and U bar B, sum over the spin. So this time I take the index explicitly and I don't contract the spinners. In fact, I write them in this order. And I sum over the spin from 1 to 2. I get K slash plus M AB. And if I do the same for the V's, I get K slash minus M. Again, these occur in Feynman diagram calculations. Okay. So, to summarize, we found 4 free particle solutions and we gave them the physical interpretation: particles spin up, particles spin down, antiparticles spin up, antiparticles spin down. Okay? If it's a Majorana spinner and you go through this exercise again, I don't know what will happen, but presumably, okay, actually this is still the same. What will happen with the Majorana spinner is that the coefficients of the U's and V's in the mode expansion will get identified. Because this is still not psi, this is just some basis of functions in terms of which we expand psi, which we are going to do right now, psi A of x. So this is the mode expansion as it's called, which we already did before for scalars. And this will enable us now, finally, to quantize the Dirac field. So, integral d3k upon 2 pi cubed 1 over root 2 omega k. That's all there. Then summation over spins equals 1 and 2. Okay. So now the U's appear with A's. So A, K with S, U, S of K. Maybe I'm being a bit inconsistent putting K here as an argument and here as a subscript. Hardly matters. Actually, this depends on all of K. E to the minus I K dot X plus so now let's think what we should have, and now we can deduce all the other terms by logic. A is the operator which destroys a particle. Okay. Now can I put a creation operator for the same particle in the same line? It's a complex field. Okay. So whatever destroys a particle, I should have something here which creates the antiparticle, because then both those actions change the charge by the same amount. So they should appear in the same line. So here I should have B dagger S K with the VK S e to the I K dot X. So this is the mode expansion for psi, and for psi we could write psi dagger or psi bar. It's nicer to write psi bar because it's the natural complex conjugation in this spinor situation. So this gives me A dagger, actually not here, probably there. So here it gives me B times V bar. Well, the bar of this term will be written here. Remember that bar also has complex conjugation, so the plus I becomes a minus I up there. So B S K V bar K S e to the minus I k dot x plus A K S U bar S. Okay. Dagger. So conceptually it looks quite similar to the case of a complex scalar field. Complex scalar field with destruction of particle, creation of antiparticle, or destruction of antiparticle, creation of particle appearing in the two places. Okay. The new feature is the U's and V's, where the U's go with particles and the V's go with antiparticles. So for a Majorana spinor, we would take B dagger to be the same. We would take this first line to be A with this and B and A dagger with V. Okay, and the second line would follow from the first because it would be real. Okay. Now to quantize, we've already said that pi A anti-commutator psi B equals I delta 3 x minus y. But we also learnt that pi A is nothing but I psi A dagger. This we saw last time. Therefore, the I cancels out and we find psi A T and x delta AB. Thank you. Minus on the right? I hope not. It has to be whatever it was before, because pi with the field has to be always the same I times delta as far as I know. Why should it be minus? Oh, that doesn't make any difference because it's an anti-commutator. If you want that, I'll do that. For
there's still an issue whether the sign on the right hand side doesn't matter.
The sign on the right hand side, I suspect it does matter.
That is what I'm asking.
I think it matters, and I think this is it. But anyway, so psi b t and y is delta 3 x minus y delta a b, and now there's a dagger in one of these. Pi is psi dagger. So this is the anti-commutation relation for the spinor field. Why has the I dropped out? We can guess that. In the usual bosonic case, Q and P is I. If I take the complex conjugate, then the Q and P order also gets interchanged because it's like a dagger. So QP goes to PQ and I goes to minus I. Here if I take the complex conjugate, this just goes to itself because in anti-commutator, the order doesn't matter. So there better not be an I on the right side. Good. Now if I impose this and ask what is the corresponding equation on oscillators, it doesn't take much to guess that we'll find A S K A dagger K prime S prime equals delta S S prime and delta 3 I guess in continuum, maybe there was a 2 pi cubed. Yes, and it's also equal to B dagger. And all other dagger, all others are 0, all other anti-commutators. So any A with any A, any B with any B, any A with any B dagger, any A dagger with any B, and what else is left? Sorry, A with B and A with A, A dagger, A, B. I think these are enough. All the others are implied by complex conjugation. There are 4 more. A dagger, B dagger, B dagger, A dagger, B dagger, and A dagger, B. All are 0. But all anti-commutators are 0, which means whenever A's and B's pass through each other, they pick up a minus sign, even though they don't pick up any commutator factor. Good. Okay, what do we expect the Hamiltonian to be? That's very simple. The Hamiltonian is always pi psi dot minus L. So it's Hamiltonian density pi, Hamiltonian under the integral d3x pi psi a dot minus L. Now interesting thing happens. Here you get I psi dagger a psi a dot. Now what is L? L is minus I gamma mu del mu of psi and then the mass term. In that one, there is a term minus I psi a dagger psi a dot and then minus I psi bar gamma I del I psi. And finally plus M. So I've split the kinetic term into 2 contributions, the time derivative and the space derivative. Now what do we see? First 2 terms cancel. So unlike bosons with second order action, where PQ dot minus L, what happens is it becomes a P squared minus half P squared. So you get half P squared at the end. The factor of 2 between this piece and this piece. Here there is no factor of 2. So these pieces just cancel and that's the Hamiltonian. And if you take that Hamiltonian and plug in the mode expansion which I just erased, you will find, not to anybody's surprise, that in momentum space it is the integral d3k over 2 pi cubed omega k sum over spins a k dagger s a s plus d k dagger plus again a possibly infinite term. What did I do?
No, I think that infinite term will be 1 half of each term.
No, because it's infinite, because again you have to sum over k.
Yes.
But it's also negative. That's an interesting fact. So a little side remark for those who are interested. If you combine a theory with fermions and bosons, then actually the infinite term can cancel if you opportunely choose your number of bosons and fermions, and that is the first of many effects due to supersymmetry. Okay, so that's just a side remark. Supersymmetric theories are the only theories where this 0 point term doesn't need to be dropped by hand. It actually cancels out mode by mode. Each k, it just cancels between bosons and fermions. So here, after removing a constant, so it's just a comment that that constant is negative in sign term by term. Okay. And perhaps I think it should be very clear that these A's have nothing to do with the A's we described earlier for bosons, right? These are fermionic A's quantized with anti-commutator. I just used the same notation. Books try to avoid it. Some books use B and D because A should not be used again. So A is reserved for bosons. So that you just should remember what control. Just as we did for bosons, the one particle state is defined as root 2 omega. So K is defined as root 2 omega K A K dagger on 0. So it has two labels, K and S. So therefore the normalization of this is 2 omega K. So K prime R K S is 2 omega K 2 pi cubed delta 3
Delta R.
sorry?
Say delta.
Delta RS. Good. Now the last thing we need to do, we're running a little bit late because I have something else also to tell you. So I'll do this quickly, is the propagator. For this, we have to modify our definition of time ordering because of the fact that fermions anti-commute. Okay? So, time ordering of psi, let's say one psi and another psi bar, is defined to be psi x, psi bar y, if x naught greater than y naught. If y naught is greater than x naught, then we want to write them in the reverse order, right? That's time ordering. But we must acknowledge that then there's a minus sign, so it is minus psi bar of y, psi of x, if this is true. There's a slight change. Okay? And these minus signs keep cropping up all over the place in calculations. Now what we want to find is the analog of Feynman propagator, T of psi A of x, psi bar B of y, 0. How can we find this? Well, we did a calculation in the scalar case. Okay, we first examined it case by case. We expanded this over its own oscillators. We commuted them. We got some integral, and then we converted that integral from d3k to d4k. Sorry, d3k to d4k to get the final form. That's all rather painful. There's a much simpler way to do it, which is to note the following. For the scalar field, this quantity also happened to be a Green's function, so this df x minus y, as you must have seen, I think in some of the tutorials at least it was done, that box minus m squared on df x minus y was delta 3 x minus y with some probably just I or minus I. Sorry, first of all it's box plus m squared, I guess, in my notation, and it is minus I. Actually, the correct thing is to say it's minus of box plus m squared. This is the Clangordin operator you get when you write the Lagrangian after one partial integration, and it acts like this. So therefore, this one, which we'll call SF, S for spinor, so it's the Feynman propagator for a spinor, should satisfy del I del slash minus m on SF equals I delta 3 x minus y. Delta 4. Thank you. Good. Now there's a very easy trick to find SF, because if I act once more on this with I del slash plus m, then I find this combination on SF is I del slash plus m on delta 4. But the left side now is the Clangordin operator. This thing is box minus box plus m squared, which I call the Clangordin operator. Okay? So we see that if I propose SF of x minus y is simply I del slash plus m acting on the old Feynman propagator, the one for scalar fields, then I'm through. I del slash, then I'm through, because now if I act with I del slash minus m on this, sorry, is this right? Yeah, this is right. Then, if I act with I del slash minus m on this, then on this side I get minus of box plus m squared, but this is the Clangordin Green's function, so that gives me I delta 3. So I'm done. This is the solution. So what I did is to solve the Fermion Feynman propagator just in terms of the scalar one. In terms of an integral representation, it's very easy. You remember that df was 1 by k squared minus m squared plus I epsilon. That this much is just df. Now if I act with this operator, it goes straight inside and differentiates the x sitting over there. So it gives me k slash plus m upstairs. And there was already an I. In df there was also an I, so I get this. So this is the answer. And in momentum space, it's just this much. This part is the momentum space. Yes. Sorry? Yeah, it solves that equation. You can just check. It solves the defining equation, this. Because if I act with that operator, I del slash minus m here, I get Clangordin operator here, which acting on this gives me delta 3x minus y. So I'm done. In momentum space, SF of k is I k slash plus m upon k squared minus m squared plus I epsilon. And this is the same as I upon k slash minus m, or people write it that way, but this is very confusing because this is 1 upon a matrix. What does it mean? Actually, it just means this. It's just shorthand for this. Why am I having I? Propagators always have an I. DF had an I. That I comes from DF. So the same. DF was I over k squared minus m squared. So this is that thing times k slash plus m. Okay. So that brings me to an end of this discussion. There is some more discussion in the notes, but I won't do it here. Now I have 25 minutes left, and I'm going to switch gears a little bit. So let me just say that this ends the relatively rigorous and precise part of the course where I did everything in detail. From now on, whatever I do will have to be a little bit sketchy because we need to collect some new ideas in order to do practical calculations. Now, one thing I think everyone noticed that has been missing from this course is that I didn't do a single computation that can be compared with an experiment. So that's still some distance away. The closest we'll get is Monday. But before that, we need to ask, what does 0t, not 0, omega t have to do with measurable quantities? This is an endpoint correlation function, and now a matrix element for scattering of an incoming state of some particles into an outgoing state. Okay, so it's actually not written as a matrix, it's written as a function of incoming and outgoing momenta. So S as a function of, let me write it in this order, let P1 and P2 be the incoming momenta, so two particles coming into an experiment. Outgoing could be any number, so this, okay, but books will often refer to this, and even in its definition, as the expectation value of the matrix element of this between the ket state P1, P2 and the bra state K1 up to Kn. So that's why it's called S matrix. This is the quantity. Nobody ever discusses S matrix involving more than two initial particles. Why? Should we? Three particle. Good. Impossible, actually. I think it's the only people who would imagine doing three particle scattering are people who have never been inside any sort of experimental, or never been near any sort of experimental equipment. Okay, we don't determine when and where two particles actually interact. We send in two beams. As and when a particle of this beam and a particle of this beam meet, they interact. If we were required at that moment to produce a third particle which interacts with these two at the same point, I think we would be pretty much done for. There's no sense in doing that. No matter how many particles we send in two beams, the actual interaction is always a particle from here and a particle from here at a time. Okay? So therefore P1, P2. This one is in our control. If we want, we can restrict to study two particle final states. And in fact, for most purposes, for today and most purposes, we do that. But we might do inclusive scattering, in which case we count everything that comes out. Very much up to us. Okay. Now, yes.
Supposing I fire a photon at an electron which is bound inside an atom. So then I have technically, that is,
not really.
incoming photon.
Yeah, okay.
Is bound electron.
Yeah.
And a virtual photon that the electron is interacting with the nucleus.
Yeah, but the virtual one doesn't count. This is all external particles. There could be any amount of virtual particles in this process.
This virtual particle is in the asymptotic state.
There can't be a virtual particle in an asymptotic state. I understand what you're saying. Okay, so combining scattering problem and bound state problem is probably very tricky. So here what we imagine always are these are unbound particles coming in from infinity. Now, schematically, we would like to write this as the overlap of a state P1, P2 which is incoming and the state K1, Kn which is outgoing. Okay? These should not be considered as states at the same time. Okay? This should be considered to be in the far past. This should be considered to be a state in the far future. Okay? Now we have some experience with this. If you remember, when we used the state omega, we defined the state omega in by acting on it with e to the minus iht and taking t to infinity. That was sending this omega to minus infinity in time, and correspondingly this one to plus infinity, and that's why they are not the same state at all. That's why the overlap omega had that exponential of interaction Hamiltonian. Okay? So you can say that exponential of interaction Hamiltonian evolves the incoming vacuum to the outgoing vacuum, and now we want to do something similar, except that what's incoming is not the vacuum but is a state containing two particles, and what's outgoing is also not the vacuum but a state containing particles. So here's the new thing. Sorry? No, there's not an S. That's exactly what I just explained. You see, it would be S if we took both the states at the same time and asked what makes one state transition to another. That would require an S. Okay? Here, this is the in state at minus infinity. This is the out state at plus infinity. S is whatever operation connects the two. So it's actually the matrix element of S is just this. Okay. Now, it's very difficult to rigorously define this quantity and to derive the expression for it, but I'll give some motivation and write down a rough answer, and it will be good enough for us to work with. So first of all, we should assume that P1, P2 in, remember this is an interacting state. Okay? That is why it's very difficult. This is not a state of the free theory, this is a state of the interacting theory. This corresponding state of the free theory we know very well. Okay? That state would be called P1, P2, 0, where 0 specifies the free theory. And what is that state? It's just A dagger of P1, A dagger of P2 acting on the vacuum. That we know. It's this one that we don't know and we have to make some intelligent guess for. And the intelligent guess, by analogy with what we've done earlier, is to put e to the minus iht and take the limit t goes to infinity 1 minus I epsilon. Okay, this sends this state into the far past, but it's still a bit tricky because this should be interacting state in the past. This is a free non-interacting state in the past, so there's some physical assumption that asymptotically the particles get so separated that they don't interact. In some theories, that assumption is violated. In conformal invariant field theories, that assumption is not valid, and those theories don't actually have an S matrix. So it's not always possible to define an S matrix. What about the out state? So from now on, I'm just going to take two particles. You can easily generalize this to n particles. Okay? So I should take this to be the free one and then multiply here with e to the minus iht and take the limit. It has to be the same operator because then the same limit sends this to minus infinity and this to plus infinity. I think you saw that in your tutorials for the vacuum, and here we are doing it for a multi-particle state. Now, you remember what manipulations we used? We introduced some e to the IH naught, we converted this to u and u dagger, then we found a differential equation for u, and then we wrote it as exponential integral of Hamiltonian, and then we had some division by some normalization, and we saw that the disconnected diagrams cancel. So I'm bypassing all those steps and assuming they can be done, and that there's a final formula Sk1, K2, P1, P2 is equal to the incoming state here, P1, P2, free, the outgoing state here, K1, K2, also free, and time order e to the minus I minus t to t, H interaction in the middle. So I am using the same recipe that I used for the vacuum for a particle state. However, as I understand, this is not as easy to justify as it is for the vacuum case. Okay? And in particular, we have not written any denominator factor to take care of the vacuum bubbles. Instead of that, we will simply drop any disconnected pieces when we calculate. We will do it manually. But you will see that the prescription becomes clearer as we go along. So this is going to be my calculational tool to find the S matrix, and this once I've written it, you can't argue about how it's to be calculated because everything in this depends only on free fields. Okay, so this is calculable by the same Feynman diagram expansion. The slight twist is that instead of the vacuum, you have a two-particle state already there. But this state, of course, is just given by two oscillators on the vacuum. I have to take care of normalizations, otherwise nothing is very difficult. Okay, so let's see what happens to lowest order. What happens to lowest order? Now it becomes very easy. To lowest order, what should I do with the middle thing? Just replace it by 1. So it's the overlap of the free state 0 with the free state 0, and this calculation is given in my notes. This part is not yet up on the web, but it will be, and it actually it involves just expanding in terms of oscillators with 2 omega factors. Ultimately you get 2 omega 1, omega P1, 2 omega P2, 2 pi to the 6 times delta. So what do you physically expect this overlap to be? Delta of what? What is the delta of P1, P2, K1, K2? How does a delta function have 4 arguments? It only used to have 1, huh? Yeah, and what is the momentum conservation? No. But no, think a little bit more clearly. These are 2 A daggers and these are 2 A's. And then vacuum to vacuum. So one of these A's has to eat up one of these A daggers and the other A has to eat up the other A dagger. And it can do it in 2 different ways. So we get delta of P1 minus K1 times delta of P2 minus K2 plus delta of P1 minus K2 delta of P2 minus K1. This is what we actually get. It's a simple exercise and it has a very simple physical interpretation. So from now, so earlier I think I had once written time going upwards, so I apologize for that. From now, time will go from right to left, which is not also my favorite convention, but you see why, because it fits, the pictures will then fit with the matrix elements, because this is the state at early time and this is the state at late time. So it's good for time to go from right to left. So here's the particle of P1 coming in. Here's the particle with P2. Here's the particle with K1 and particle with K2. And it's either this or it's that. 2 diagrams. Right? Fine? In other words, both the particles go through to the final state. Either they map onto the final particles as K1 equals P1, K2 equals P2, or they are flipped. But notice something a little bit surprising. These are Feynman diagrams, but do you see any propagator in the expression? There is no propagator in the expression. That's the answer for this matrix element. Okay, this Feynman diagram represents the answer correctly, but we realize that there are no propagators for the external particles. What's the basic reason? Sorry? No, that's okay. There are no vertices is not the problem. If you expand, okay, that's, well, let me put it this way. The real reason is that you already prepared a state at minus infinity. So this state is not prepared by the field phi. Rather, this is directly created by the oscillators A dagger and A dagger. So as a technical reason, this is just created by oscillators, this is just created by oscillators. There's no field in this. Okay, just single modes. Okay, so there's nowhere that T of phi x, phi y will come in. That's why there's no propagator. Okay, this is actually a good feature, and we'll see that it persists to all orders. Okay, so now this is where particles just went through, they didn't scatter. The scattering matrix is measuring scattering. If scattering doesn't happen, then why call it a scattering matrix? T, where the I is put in for reasons of convention, but they are useful. The 1 represents all situations of no scattering. And T represents everything else. Okay, I'm writing it informally, but as we calculate, whenever we get a contribution, we'll decide whether the contribution should belong to 1 or to T. This contribution certainly should belong to 1. You would think it's the only one, but actually there are more. Okay, so and take this down to the first order. So we encounter K1, K2, integral phi fourth, P1, P2 with a T and lambda over 4 factorial with a minus I. Now something interesting happens. You see, you cannot just use Wick's theorem directly because it's not a vacuum to vacuum amplitude, but you can use the fact that T of phi fourth of y was equal to normal ordered product phi fourth of y plus phi squared of y normal ordered times the propagator from y to y squared plus the propagator from y to y, one propagator here and 2 here. And this came with a coefficient 6 and this came with a coefficient 3. This all we've done, so I'm not repeating the counting. So this term, actually, if it would have been vanishing between vacuum to vacuum because of the definition of normal ordering, but it's not vanishing between 2 particle to 2 particle state. In fact, it's simple to check that between a 2 particle to 2 particle state, the only term of phi fourth which does contribute is the one which destroys these 2 particles and then creates back 2 particles. And what term is that? Supposing I expand phi as phi minus plus phi plus, which I did last time, which term destroys 2 particles and creates back 2 particles in phi to the fourth? Phi minus squared, phi plus squared. This term is non-zero and all other terms are 0. And what is the coefficient of this in the expansion of phi to the fourth? If I take the 4th power of this, with what coefficient do I get phi minus squared, phi plus squared? Very good. 6. Okay. Now that this is equal to 6 times Yes. Yes, what was the question? Yeah. 5 plus is the, which one is 5 plus and which one is 5 minus? I think 5 plus is the destruction. I don't know why, but I think that is it. It should be destruction first, no? Normal ordering does what? It puts destruction operators on the right. So when there's a term with 2 5 minuses and 2 5 pluses, I believe it's 5 plus which goes to the right. If I'm wrong, you can change my conventions, but I believe this is right. It's normal order. Yeah. Okay. So the claim is that you get 24. Out of that, 6 is from here, and you get 4 more from 2 of these and 2 of these. You'll get 4 if you do this calculation, and it's done in the notes. Okay. So at the end of the day, we plug that back over here, and we find that this contribution, that is the this contribution, 5/4 normal ordered contribution to S is minus I lambda delta of momentum conservation. That's the full contribution for that term. Okay? So this contribution, first of all, it is of order lambda. It does involve scattering. And notice that it has only one delta function and not 2 delta functions. Okay? Which means that the momenta are allowed to rearrange themselves, subject only to that delta function. The previous term, which I dropped because it was trivial, had matched the incoming momenta one by one to the final one, but in this term there's only a single delta function, so the momenta can move around. Okay? Good. So this is very good, and this motivates us to extract out I, there's also 2 pi to the 4th. This motivates us to define this T as I 2 pi to the 4th delta for delta 3 for 3 of, these are delta 3s or delta 4s? Delta 4s, I think. All of these are delta 4s actually. So they should not have this on top. So we'll always find an I, we'll always find 2 pi to the 4th, we'll always find delta 4th from every term. So whatever is left we call M. And so we learn that M, this is the scattering matrix element if you like, it's called M. It's a non-trivial part of the S matrix after momentum conservation and some pi's are removed, and we find that M is equal to minus lambda. That's just from this term. We still have to analyze those 2 terms. So let's see what the other 2 terms give. Diagrammatically, it's very easy to see. If we look at these terms, we see that diagrammatically they look like this. This one, so this one if you like, is just a propagator from the point to itself, and this term connects that same point y to the external lines. And so it will be like this. This is one possibility. The other possibility will be, or well, there will be altogether 4. Another possibility will be this. Another possibility will be that they cross, and then one of them has a bubble. And the other possibility will be that they cross, but the other one has the bubble. Okay? These are 4 terms that are contained in the middle thing. Now, would you call this trivial or non-trivial scattering? There is no scattering. So this also should go into 1. This is why 1 is a bit of a complicated object. It doesn't only include free propagation, but also all self-interacting propagation, so long as the propagation is from a particle to a particle without interacting with the other particle. So this also goes into 1. So we forget it. And this is just the vacuum bubble, that figure of 8, which is disconnected from everybody. So in this one, the particles propagate through and the bubble sits somewhere else. So that, of course, is the kind of thing that we certainly should ignore. So that also we throw into 1. So finally we learn that to lowest order, m is minus lambda. And we've learnt a very, very important result. Physical meaning of the coupling. It is the non-trivial part of S matrix. 2 by 2 to 2 S matrix, 2 particle to 2 particle S matrix to lowest order. And with a minus sign, that's not very important. So minus, the coupling is minus of m. But this, for the first time, reveals the physical meaning of the coupling constant. And now I'll stop with one final comment, which is that, again in this, there are no propagators. This is the full momentum dependence of the answer. There is not one propagator for each external leg. So there never is any propagator for external legs when we calculate the S matrix. So S matrix equals correlation function with external propagators dropped, or in surgical language, amputated. And on Monday, we'll see an example explicitly where we'll calculate an S matrix term. So the external propagators are dropped and external momenta are on shell. That means all the external particles now are real physical particles with k squared equals m squared. Notice that only after dropping the external propagators, we could put k squared equals m squared, because what are the external propagators? They are 1 over k squared minus m squared. So if we didn't drop them and we tried to put k squared equals m squared, we'd just get infinity and we wouldn't know what to do. But the S matrix prescription tells us to first drop them, because it says they don't appear in the calculation. Okay, so now we are free to put k squared equals m squared because the external propagators are not there. So in that sense, all the particles that contribute to the S matrix are all virtual. Anything that's real, we drop its propagator. So all propagators in this calculation would be virtual. And to lowest order at tree level here, there's no propagator at all. This is just the answer. Okay, so that's a sort of bare bones picture of how the S matrix works, and with that I will stop here.
How do you